Today we will talk on the floating horizon algorithm in the for hidden surface removal. And if you remember last time I had mentioned that if you have a curve or if you have a surface of the type f of x y z equal to 0, then we can use this floating horizon algorithm. If you look at this coordinate system and we are looking at the curve from the z direction, let us say, what we will do is we will first take planes parallel to the xy plane, and the first plane that we will take will be the closest to the eye. If I am looking at it from this side, this is the first plane that we will take, the next plane will be just behind that, the one after that will be further behind. And if we have a surface given by this, we can get the equation of a curve as we will see it in each successive plane. If I see the intersection of the first plane with this surface, I might get a curve of the form like a curve something like this. This is the curve for the intersection with the first plane. Then we take the intersection with the next plane, okay, the one that is slightly behind. Okay, if the next intersection comes something like this, we can draw that again, and this way we will keep taking successive planes and their intersections with this surface. Now if we have a situation in which the first curve that we draw is a curve like this, and the next curve that we get intersects this curve, okay, that means the first it goes like this and intersects it here like this and goes on further. In this situation, if you look at this figure, we are looking at the surface from the front. Okay, since we are looking at the surface from the front, if the curve for the second plane is cutting the curve for the first plane, okay, that means the curve for the second plane is at a lower height. Okay, so if this curve is at a lower height, in that case we will get this curve to be intersecting as we are getting here, and since it is at a lower height, that means this portion of the curve is going to be hidden. Okay, this way we will keep drawing these curves one after another, and the portions which are hidden will come as or will come at a lower y value. This is in the xy plane, x, and this is y. Okay, in the xy plane the curve will come at a lower height. Okay, this is the curve from the first plane, this is the curve from the second plane, and this is the basic principle we will use in the floating horizon. What we will do is, along the x axis, we will, let us say this is my x axis, I will divide this into portions like this. Okay, well, let us say each of this mark corresponds to the next pixel, okay, or whatever resolution we choose. So let us say at each x value we can compute the y value that has been displayed. Okay, that y value is in some sense this is the level of the horizon that we are seeing right now. That means as we are going for successive planes, okay, we took the first plane, then we took the second plane behind and the third plane behind that, and so on. That means we are slowly shifting the horizon backwards, and as we are shifting the horizon backwards, the current y value at each point, that will tell us the current position of the horizon. Okay, if we get any entity which is above this horizon, that will be visible. If any entity is below this horizon, it will not be visible. Okay, think of if you are looking at a set of hills. Okay, you have a hill in front, and if you have another hill behind it, you can see that only if its height is higher than the height of the first hill. Okay, that is exactly what we are doing here. Okay, so we will, let us say, maintain an array called horizon of x, and this will store the current y max value. That means, let us say, if this is and so on. Let's say the horizon at 1 will store the current Ymax value, which is this. Horizon of 2 will store the Ymax value, which is this. Okay, the horizon at 5 will store the Ymax value here. Okay, and if when I am drawing the next curve, let's say my next curve is like this, then the y value of the curve at this point is lower than the horizon at this point. Okay, so this curve is hidden at this point. Okay, similarly the y value for the curve here is lower than the horizon of 2. Okay, so here also this curve is hidden. Okay, at this point the two are same, so the horizon will be retained, and here the y value is greater than the horizon, so I will update the horizon to this value. Okay, in this position the curve will become visible, and so on. Okay, so this way we will be maintaining an array called horizon, which will store the current highest curve visible, or current highest curve that has been displayed. Okay, and any curve which is displayed after that will be displayed only if its Ymax or if its y value is greater than the Ymax value stored at that point. Okay, so let us write down this algorithm. Again? Again?
We will be differentiating between the different hills by their color or intensity.
That
This is you get a one simple hill.
see, if you have one single surface to be displayed, okay, then possibly all these curves will have the same color or intensity. Okay, if you have a number of surfaces, then you can have them have different colors for that. Okay, so in this case, right now I am talking about only one single surface, and all these curves are obtained by the intersection of the single surface. Okay, I have a complicated surface like this, and I am taking intersection with the vertical plane. Okay, so I will get in every plane I am getting only one curve right now.
What I am saying is in the final picture, how will you come to know that the curve is coming from different planes? It will look like just a simple continuous curve.
Each curve will look like a continuous curve, but we will have a set of curves. One curve, the next curve, and so on. Maybe I will. Are you able to see this figure? See, if you look at the first curve that has been drawn, this curve, this is the intersection with the first plane. The second curve that has been drawn is the intersection with the second plane, and so on. So this is the kind of effect you will have. Is that okay? Okay, let's go back to the algorithm. We'll come back to the figure later on. Okay. The first step is that we've taken a set of planes, and for each of these planes we've got a curve. Okay, that curve is of the form of this. Okay, essentially what we are doing is we are rewriting this as y is equal to f of xz. Okay, because we want to compute the y value for the different curves at different x and z locations. Okay, and then we are taking z equal to constant curves. Okay, so we are getting a family of curves, and we have to display this family of curves, okay, or this set of curves. So first thing we will do is sort all curves as per the z value or as per z coordinate. Okay, the one closest to the eye will be the first curve that we will consider, and the one furthest from the eye will be the last curve. Okay. Then
What
Yeah.
do you mean by sorting these curves? We don't have any available set of curves, do we? I mean, this will be.
we'll arrange them in the decreasing z order in this case. That's all.
I mean, this will be automatically incorporated as the program being written.
Yeah. So this is a part of the program that I'm giving the algorithm for that. Right? The first step would be that all the curves that you're getting, you have to treat them in the decreasing z order. The one closest to the eye, then the one after that, and so on. Okay. Start by the z equal to constant curve closest to the eye. Okay, and now if we have taken the first curve, that is the one that is closest to the eye, and for this curve for the first curve we will examine the y value at each successive locations. Okay. And we will compare this y value with the current value of the horizon. We will compute y equal to f of xz, okay, that is the y value at the current x location, and if this y value is less than the horizon, okay, then the curve is hidden. Okay, and if y value is greater than the horizon of x, then we will say that the curve is visible, we will display the curve and we will update the horizon. Let us say horizon of x will be equal to y.
So,
Yeah.
shouldn't we be at every value of x storing the highest as well as the lowest point?
I'm coming to that. I'm coming to that. Right now I'm just you think of, at the moment you think of this surface. Let's say if this is my surface. So think of it as a solid surface with a complete solid under it. Okay. If it is just a planar surface, by planar I mean just a sheet kind of surface, then what will happen is the surface might be going underneath like this, and you might be able to see the surface from under it. For that I'll modify it accordingly. I'll come to that. Okay. So if at any x value we compute the y value, and if the y value is less than the horizon of x, then the curve is hidden. If the y value is greater than the horizon of x, then the curve is visible, and we'll update the horizon of x to y. Okay, we are doing it for all the x values, and we'll repeat it for all the curves successively one after another. Okay, so by this we will be able to display all these curves one after another, and we'll get a 3D effect the way we just saw in the figure. Okay. Look at this figure. Is z1 equal to constant at the first curve, then you have z2 equal to constant, z3 equal to constant, and then at z4 equal to constant, a part of the curve is going underneath. Okay, that has been shown as a dotted line. That is this part of the curve. And again z5 equal to constant is again going dotted. Okay. So this way, by taking successive planes, we are able to get a three-dimensional kind of effect by showing the back portion of this hillock as dotted lines. Again, as someone said, in this hillock, we are assuming that this is a solid surface. Okay, that means it is complete solid under it. If it is not, if it is a thin surface, in that case, the surface might go underneath, like if you are seeing it from front, the surface might go underneath like this, and from there you will be able to see the lower portion of the surface. Okay, that we have not been able to incorporate right now.
Like the previous figure that you have shown us.
That was in the previous figure that had been incorporated. Okay, this has been incorporated in this figure. Okay, how is that incorporated? I'll just explain that. By incorporating that, what we do in this, right now we are maintaining an array called horizon of x. Okay, now this horizon is essentially the upper value of y that is visible. Okay, we are assuming that everything is solid under it. Okay, but if it is not, then we also need to maintain the lower value of y which is visible. Okay, so if I maintain the lower value also, that means I maintain two horizons. Horizon upper of x as well as horizon lower of x. Okay, and if my curve happens to go below the horizon lower, okay, let's say if you are looking at a surface from front, if any curve happens to go below the lower horizon, this is my lower horizon right now, if this part of the surface goes below that, then you will be able to see it from front. Okay. So we will maintain a horizon lower as well as a horizon upper. And how do we take care of that? In this algorithm, we will change this step, and what we will do is, we will say if y is less than horizon lower of x, okay, then also the curve is visible, and we will update horizon lower. Okay, and if y is greater than the horizon upper, sorry, then of course curve is visible, and we will say horizon upper of x will be equal to y. Okay, so we maintain two arrays, one is horizon lower and the other is horizon upper. Okay, by doing that we will be able to display thin surfaces. Okay, surfaces which can also become visible from underneath. Okay, any questions on this algorithm so far?
This is only for rays parallel to the z axis.
This is only when the viewing direction is the z axis. Okay, I am looking at it from the z equal to infinity direction.
The figure shown there slightly tilted, it was not exactly.
In the figure shown, this figure?
Yeah.
Why? This is the z axis in this case. See, whatever my viewing direction be, I can always rotate my coordinate frames so that the viewing direction becomes the z axis. Okay. You have seen transformations, right? Okay, so whatever my viewing direction be, I can always rotate my coordinate system so that the viewing direction becomes the z axis, and then I will apply this algorithm. Okay, whenever we are talking of these hidden surfaces algorithm, we normally take the viewing direction to be the z axis. If we are actually looking at the object from some other angle, we rotate our coordinate system such that the viewing direction will coincide with the z axis. Okay, if I am looking at the object from this side, okay, then I'll make this my z axis, I'll rotate my coordinate system accordingly and then redefine the plane. Okay. So any question on this algorithm so far? Okay. Now this algorithm we've so far been applying for cases where the surfaces can be represented in this mathematical form. Okay, that means my surface can be represented by a mathematical equation like this. Okay, often what happens is surfaces are not represented in a mathematical form, but they are represented by interpolation. Okay, that means if you look at this xy plane, then my curve, earlier I was taking my curve to be a smooth curve like this. Instead of this, my curve might be a set of points. And between these points I might be interpolating. Okay, that means this curve or this surface is available as a set of discrete data and not in the form of a mathematical equation. Okay. If this curve is not a mathematical equation like this, but is a set of discrete data points, okay, then this algorithm might not be directly useful. Okay, because let's say my one curve is like this. Now the next curve is again a set of straight lines which might be something like this. These are my data points for the next curve. Okay. So typically what can happen is that at some discrete points my surface has been digitized. Okay, that means that let's say some values x1, x2, so on, at each of these values xi's, a surface is known. That means for the first surface, that is, this is the z equal to z1, this is z equal to z2. For each of these z values, the y values are known as discrete points. Okay, for a case like this, we can use the same algorithm with a very minor modification, that instead of considering the y value at each xi's, we will consider only at the data points. Okay, I mean show it in a different figure. For the z equal to z1 curve is given by these set of data points. The z equal to z2 curve is given by these points in green. Okay, in this case we cannot draw a straight line like this or like this. What we will have to do is between these 2 points we will interpolate, and wherever the intersection lies we will draw a straight line up to that point, and then the rest would be dotted. Okay, similarly we will continue from here like this and this would be dark. Similarly, in this portion, we go like this, and this would be dark. Okay, we'll carry out an interpolation, and while interpolating, we'll find the intersection of this line and the intersection of this line. Okay, and up to the intersection point, the curve will be visible, and either after that or before that, and that we will decide whether it is invisible or visible. Okay, so what we will do is, these are the points x1, let's say this is xi and this is xi plus 1, and we will maintain the horizon at each of these xi's. Okay, so we will maintain the horizon at x, and when we have displayed a curve or a set of curves, the next curve when we are displaying, let's say for this point and for the next point, we will compute y at xi and y at xi plus 1. Okay, we will decide whether the curve is visible at at xi and at xi plus 1. If the curve is visible at both the points, okay, that means that, let's say if we have a data points like this, both these points are visible, then the complete curve is visible. Okay, so if this is visible, this is also visible, then complete curve is visible. Okay, if at xi the curve is visible and at xi plus 1 the curve is invisible, okay, in that case, from xi to the intersection point, the curve will be visible, and from the intersection point to xi plus 1, the curve will be invisible. It will not be visible. Okay. On the other hand, if xi is invisible and xi plus 1 is visible, it will be the other way around. From xi to I to the intersection point, the curve will not be visible, and from I to xi plus 1, the curve will be visible. And of course, if both of them are invisible, in that case the curve is invisible. Just 1 minute. Okay. But if a surface is available in the form of a set of data points, then our algorithm will become much more complex. Okay, not only because I have to compute the intersections, but also because, let's say after the first intersection is computed, okay, my curve is becoming like this. Okay, that means earlier my data points I was taking them at this level and at this level, but after this intersection my data point will also have to be taken here. Okay, because the horizon in this portion can be found out by linear interpolation. Between this portion also it can be found out by linear interpolation. Okay, but I cannot just take the horizon here and the horizon here. Okay, so I'll have to add this to the data point and then proceed from that point. Okay, so if the surface is available to me in the form of data points, then the algorithm becomes slightly complex, but it can be taken care of. Okay, you're saying something.
So like these data points are assuming to be given with constant x, like they're not the data point for a next curve not given for in between x's.
Yeah, normally that would be the case. If it is given at random values,
Yeah, then it will be.
then the algorithm will become even more complex. Okay, well then you have to take a set of planes and compute the value of the curve at all those x values. Okay. Right now, assuming that it is available at a set of data points. Okay. Any other question on this algorithm? Okay, on this floating horizon algorithm. Okay, in that case, I think I'll stop here now. As far the hidden surface removal is concerned, that is all that I'm going to cover. From the next lecture onwards, we'll be talking of finite element method. Okay, and that will basically be talking of how to compute stresses and displacements for any given object using the finite element approach. Okay, so we'll start from that in the next class.